This chapter discusses conceptual data modeling using the EER model and UML Class Diagram. It is based upon our book, Principles of Database Management, published by Cambridge University Press. You can find more information about our book on the website at the bottom of my slide. My name is Bart Bausens, and I'm one of the authors of the book. In this chapter, we start by zooming out and review the database design process. We elaborate on conceptual, logical, and physical database design. We continue the chapter with conceptual design, which aims at elucidating the data requirements of a business process in a formal way. We discuss three types of conceptual data models: the ER model, the EER model, and the UML class diagram. Each model is first defined in terms of its fundamental building blocks. Various examples are included for clarification. We also discuss the limitations of the three conceptual data models and contrast them in terms of their expressive power and modeling semantics. Designing a database is a multi-step process as illustrated in this figure. It starts from a business process. As an example, think about a B2B procurement application, invoice handling process, logistics process, or salary administration. The first step is requirement collection and analysis, where the aim is to carefully understand the different steps and data needs of the process. The information architect will collaborate with the business user to elucidate the database requirements. Various techniques can be used, such as interviews or surveys with end users, inspections of the documents which are used in the current process, etc. During the conceptual design, both parties try to formalize the data requirements in a conceptual data model. As mentioned before, this should be a high-level model, meaning it should be both easy to understand to the business user and formal enough to the database designer who will use it in the next step. The conceptual data model must be user-friendly and preferably have a graphical representation such that it can be used as a handy communication and discussion instrument between both information architects and business users. It should be flexible, such that new or changing data requirements can be easily added to the model. Finally, it must be DBMS or implementation independent, since its only goal is to adequately and accurately collect and analyze data requirements. Obviously, this conceptual model will also have its limitations, which should be clearly documented and followed up during application development. Once all parties have agreed upon the conceptual data model, it can be mapped to a logical data model by the database designer during the logical design step. The logical data model is based upon the data model used by the implementation environment. Although at this stage it is already known what type of DBMS, for example RDBMS, OODBMS, etc., will be used, the product itself, such as Microsoft, IBM, or Oracle, has not been decided yet. As an example, consider a conceptual EER model which will be mapped to a logical relational model since the database will be implemented using an RDBMS. The mapping exercise can result in a loss of semantics, which should be properly documented and followed up during application development. It might be possible that additional semantics can be added to further enrich the logical data model. Also, the views of the external data model can be designed during this logical design step. In a final step, the logical data model can be mapped to an internal data model by the database designer. The DBA can also give some recommendations regarding performance during this physical design step. In this step, the DBMS product is known, The DDL is generated and the data definitions are stored in a catalog. The database can then be populated with data and is ready for use. Again, any semantics lost or added during this mapping step should be documented and followed up. The entity relationship, ER model, was introduced and formalized by Peter Chen in 1976. It is one of the most popular data models for conceptual data modeling. The ER model has an attractive and user-friendly graphical notation. Hence, it has the ideal properties to build a conceptual data model. We start by discussing the key building blocks of the ER model: entity types, attribute types, relationship types, weak entity types, and ternary relationship types. We conclude this section with examples and limitations of the ER model. An entity type represents a business concept with an unambiguous meaning to a particular set of users. Examples of entity types are supplier, student, product, or employee. An entity is one particular occurrence or instance of an entity type. Deli wines, best wines, and ad fundum are entities from the entity type supplier. In other words, an entity type defines a collection of entities that have similar characteristics. When building a conceptual data model, we focus on entity types and not on individual entities. In the ER model, entity types are depicted using a rectangle as illustrated in the figure for the entity type supplier. An attribute type represents a property of an entity type. As an example, name and address are attribute types of the entity type supplier. A particular entity, such as deli wines, has a value for each of its attribute types. For example, its address is 240 Avenue of the Americas. Hence, an attribute type defines a collection of similar attributes, or an attribute is an instance of an attribute type. This is illustrated in the figure. The entity type supplier has attribute types subnumber, supplier number, subname, supplier name, subaddress, supplier address, subcity, supplier city, and substatus, supplier status. Entities then correspond to specific suppliers, such as supplier number 21, Deli Wines, together with all its other attributes. In the ER model, we focus on attribute types and represent them using ellipses, as illustrated in the figure for the entity type supplier and attribute types subnumber, status, and date of birth. In what follows, we elaborate further on attribute types and discuss domains, key attribute types, simple versus composite attribute types, single-valued versus multi-valued attribute types, and derived attribute types. A domain specifies the set of values that may be assigned to an attribute for each individual entity. A domain for gender can be specified as having only two values, male and female. Likewise, a date domain can define dates as day followed by month followed by year. A domain can also contain null values. A null value means that a value is not known, not applicable, or not relevant. It is thus not the same as the value 0 or an empty string of text. Think about a domain email address, which allows for null values in case the email address is not known. By convention, domains are not displayed in an ER model. A key attribute type is an attribute type whose values are distinct for each individual entity. In other words, a key attribute type can be used to uniquely identify each entity. Examples are supplier number, which is unique for each supplier, product number, which is unique for each product, and social security number, which is unique for each employee. A key attribute type can also be a combination of attribute types. As an example, suppose a flight is identified by a flight number. However, the same flight number is used on each day to represent a particular flight. In this case, a combination of flight number and departure date is needed to uniquely identify flight entities. It is clear from this example that the definition of a key attribute type depends upon the business setting. Key attribute types are underlined in the ER model as illustrated in the figure. A simple or atomic attribute type cannot be further divided into parts. Examples are supplier number or supplier status. A composite attribute type is an attribute type that can be decomposed into other meaningful attribute types. Think about an address attribute type, which can be further decomposed into attribute types for street, number, zip code, city, and country. Another example is name, which can be split into first name and last name. The figure illustrates how the composite attribute types address and name are represented in the ER model. A single valued attribute type has only one value for a particular entity. An example is product number or product name. A multi-valued attribute type is an attribute type that can have multiple values. As an example, email address can be a multi-valued attribute type in case a supplier can have multiple email addresses. Multi-valued attribute types are represented using a double ellipsis in the ER model as illustrated in the figure. A derived attribute type is an attribute type which can be derived from another attribute type. As an example, age is a derived attribute type since it can be derived from birth date. Derived attribute types are depicted using a dashed ellipsis as shown in the figure. In what follows, we zoom in on relationship types. We first define them and then discuss degree and roles, cardinalities, and relationship attribute types. A relationship represents an association between two or more entities. Consider a particular supplier, for example, Deli Wines, supplying a set of products, for example, products number 119, 178, and 289. A relationship type then defines a set of relationships among instances of one, two, or more entity types. In the ER model, relationship types are indicated using a rhombus symbol. Basically, the rhombus can be thought of as two adjacent arrows, pointing to each of the entity types specifying both directions in which the relationship type can be interpreted. The figure shows the relationship types applies between the entity type, supplier, and product. A supplier can supply products, as indicated by the downwards arrow, and a product can be supplied by suppliers, as indicated by the upwards arrow. Each relationship instance of the supplies relationship type relates one particular supplier instance to one particular product instance. However, similar to entities and attributes, individual relationship instances are not represented in an ER model. The degree of a relationship type corresponds to the number of entity types participating in the relationship type. A unary or recursive relationship type has degree 1. A binary relationship type has 2 participating entity types, whereas a ternary relationship type has 3 participating entity types. The roles of a relationship type indicate the various directions that can be used to interpret it. The figure represents a binary relationship type since it has 2 participating entity types, supplier and product. Note the role names sub-prod and prod-sub, which we have added in each of the arrows making up the rhombus symbol. Here you can see 2 other examples of relationship types. The supervisor's relationship type is a unary or recursive relationship type which models the hierarchical relationships between employees. In general, the instances of a unary relationship relate 2 instances of the same entity type to one another. The role names supervises and supervised by are added for further clarification. The second example is an example of a ternary relationship type, booking, between the entity types tourist, hotel, and travel agency. Each relationship instance represents the interconnection between one particular tourist, hotel, and travel agency. Role names can also be added, but this is less straightforward here. Every relationship type can be characterized in terms of its cardinalities, which specify the minimum or maximum number of relationship instances that an individual entity can participate in. The minimum cardinality can be either 0 or 1. If it's 0, it implies that an entity can occur without being connected through that relationship type to another entity. This can be referred to as partial participation, since some entities may not participate in the relationship. If the minimum cardinality is 1, an entity must always be connected to at least one other entity through an instance of the relationship type. This is referred to as total participation or existence dependency, since all entities need to participate in the relationship, or in other words, the existence of the entity depends upon the existence of another. The maximum cardinality can either be 1 or n. In case it's 1, an entity can be involved in only one instance of that relationship type. Or in other words, it can be connected to at most one other entity through that relationship type. In case the maximum cardinality is n, an entity can be connected to at most n other entities by means of the relationship type. Note that n represents an arbitrary integer number bigger than 1. Relationship types are often characterized according to the maximum cardinality for each of their roles. For binary relationship types, this gives 4 options: 1 to 1, 1 to n to 1, and m to n. Here you can see some examples of binary relationship types together with their cardinalities. A student can be enrolled for minimum 1 and maximum m courses. Conversely, a course can have minimum 0 and maximum n students enrolled. This is an example of an n to m relationship type, also called many-to-many relationship type. A student can be assigned to minimum 0 and maximum 1 master thesis. A master thesis is assigned to minimum 0 and maximum 1 student. This is an example of a one-to-one relationship type. An employee can manage minimum 0 and maximum n projects. A project is managed by minimum 1 and maximum 1, or in other words, exactly 1 employee. This is an example of a one-to-n relationship type, also called one-to-many relationship type. Like entity types, a relationship type can also have attribute types. These attribute types can be migrated to one of the participating entity types in case of a one-to-one or one-to-n relationship type. However, in case of an m-to-n relationship type, the attribute type needs to be explicitly specified as a relationship attribute type. You can see this illustrated in the figure. The attribute type hours represents the number of hours an employee worked on a project. Its value cannot be considered as the sole property of an employee nor of a project. It is uniquely determined by a combination of an employee instance and project instance. Hence, it needs to be modeled as an attribute type of the works on relationship type, which connects employees to projects. A strong entity type is an entity type that has a key attribute type. In contrast, a weak entity type is an entity type that does not have a key attribute type of its own. More specifically, entities belonging to a weak entity type are identified by being related to specific entities from the owner entity type, which is an entity type from which they borrow an attribute type. The borrowed attribute type is then combined with some of the weak entity's own attribute types, also called partial keys, into a key attribute type. Let's illustrate this with an example. The figure shows an EER model for a hotel administration. A hotel has a hotel number, HNR, and a hotel name, HName. Every hotel has a unique hotel number. Hence, HNR is the key attribute type of hotel. A room is identified by a room number, RNR, and a number of beds. Within a particular hotel, each room has a unique room number, but the same room number can occur for multiple rooms in different hotels. Hence, RNR as such does not suffice as a key attribute type. Consequently, the entity type room is a weak entity type, since it cannot produce its own key attribute type. More specifically, it needs to borrow HNR from hotel to come up with a key attribute type, which is now a combination of its partial key RNR and HNR. Weak entity types are represented in the EER model using a double-lined rectangle as illustrated in the figure. The rhombus representing the relationship type through which the weak entity type borrows a key attribute type is double-lined as well. The borrowed attribute type or attribute types are underlined using a dashed line. Since a weak entity type needs to borrow an attribute type from another entity type, it will always be existence dependent on the latter. In our previous example, room is existence dependent on hotel, as also indicated by the minimum cardinality of 1. Note, however, that an existence dependent entity type does not necessarily imply a weak entity type. Consider the example in this figure. The purchase order entity type is existence dependent on supplier as indicated by the minimum cardinality of 1. However, in this case, purchase order has its own key attribute type, which is purchase order number, PONR. In other words, purchase order is an existence dependent entity type, but not a weak entity type. The majority of relationship types in an EER model are binary or have only two participating entity types. However, Higher order relationship types with more than two entity types, known as ternary relationship types, can occasionally occur, and special attention is needed to properly understand their meaning. Assume that we have a situation where suppliers can supply products for projects. A supplier can supply a particular product for multiple projects. A product for a particular project can be supplied by multiple suppliers. A project can have a particular supplier supply multiple products. The model must also include the quantity and due date for supplying a particular product to a particular project by a particular supplier. This is a situation which can be perfectly modeled using a ternary relationship type, as you can see in this figure. A supplier can supply a particular product for 0 to n projects. A product for a particular project can be supplied by 0 to n suppliers. A supplier can supply 0 to n products for a particular project. The relationship type also includes the quantity and due date attribute types. An obvious question is whether we can also model this ternary relationship type as a set of binary relationship types as shown here. We decompose the ternary relationship type into the binary relationship types: supplies between supplier and project, can supply between supplier and product, and uses between product and project. We can now wonder whether the semantics of the ternary relationship type is preserved by these binary relationship types. To properly understand this, we need to write down some relationship instances. Say we have two projects. Project 1 uses a pencil and a pen, and Project 2 uses a pen. Supplier Peters supplies the pencil for Project 1 and the pen for Project 2, whereas supplier Johnson supplies the pen for Project 1. The figures show the relationship instances for both cases. At the top of the figure are the relationship instances that would be used in a ternary relationship type supply. This can be deconstructed into the three binary relationship types: supplies, uses, and can supply. From the supplies relationship type, we can see that both Peters and Johnson supply to Project 1. From the can supply relationship type, we can see that both can also supply a pen. The uses relationship type indicates that Project 1 needs a pen. Hence, from the binary relationship types, it is not clear who supplies the pen for Project 1. This is, however, clear in the ternary relationship type, where it can be seen that Johnson supplies the pen for Project 1. By decomposing the ternary relationship types into binary relationship types, we clearly lose semantics. Furthermore, when using binary relationship types, it is also unclear where we should add the relationship attribute types, such as quantity and due date. Binary relationship types can, however, be used to model additional semantics. This figure shows another example of a ternary relationship type between three entity types: instructor with key attribute type INR, representing the instructor number; course with key attribute type CNR, representing the course number; and semester with key attribute type SEM-year, representing the semester year. An instructor can offer a course during 0 to n semesters. A course during a semester is offered by 1 to n instructors. An instructor can offer 0 to n courses during a semester. In this case, we also added an extra binary relationship type qualified between instructor and course to indicate what courses an instructor is qualified to teach. Note that, in this way, it is possible to model the fact that an instructor may be qualified for more courses than the ones he or she is actually teaching at the moment. Another alternative to model a ternary relationship type is by using a weak entity type, as you can see here. The weak entity type supply is existence dependent on supplier, product, and project as indicated by the minimum cardinalities of 1. Its key is a combination of supplier number, product number, and project number. It also includes the attribute types quantity and due date. Representing a ternary relationship type in this way can be handy in case the database modeling tool only supports unary and binary relationship types. Here you can see the EER model for a human resources administration. It has 3 entity types: employee, department, and project. Let's read some of the relationship types. An employee works in minimum 1 and maximum 1, or does exactly 1 department. A department has minimum 1 and maximum n employees working in it. A department is managed by exactly 1 employee. An employee can manage 0 to 1 departments. A department is in charge of 0 to n projects. A project is assigned to exactly 1 department. An employee works on 0 to n projects. A project is being worked on by 0 to m employees. The relationship type works on also has an attribute type hours, representing the number of hours an employee worked on a project. Also note the recursive relationship type to model the supervision relationships between employees. An employee supervises 0 to n employees. An employee is supervised by 0 to 1 employees. This figure shows another example of an EER model for a purchase order administration. It has 3 entity types: supplier, purchase order, and product. A supplier can supply 0 to n products. A product can be supplied by 0 to m suppliers. The relationship type supplies also includes the attribute types purchase price and the live period. A supplier can have 0 to n purchase orders on order. A purchase order is always assigned to 1 supplier. A purchase order can have 1 to n purchase order lines with products. Conversely, a product can be included in 0 to m purchase orders. In addition, the relationship type PO line includes the quantity of the order. Also note the attribute types and key attribute types of each of the entity types. Although the EER model is a very user-friendly data model for conceptual data modeling, it also has its limitations. First of all, the EER model presents a temporary snapshot of the data requirements of a business process. This implies that temporal constraints, which are constraints spanning a particular time interval, cannot be modeled. Some example temporal constraints which cannot be enforced are: a project needs to be assigned to a department after 1 month. An employee cannot return to a department of which he previously was a manager. An employee needs to be assigned to a department after 6 months. A purchase order must be assigned to a supplier after 2 weeks. These rules need to be documented and followed up with application code. Another shortcoming is that the EER model cannot guarantee the consistency across multiple relationship types. Some examples of business rules which cannot be enforced in the EER model are: an employee should work in a department that he or she manages. employees should work on projects assigned to departments to which the employees belong, and suppliers can only be assigned to purchase orders for products they can supply. Again, these business rules need to be documented and followed up with application code. Furthermore, since domains are not included in the ER model, it is not possible to specify the set of values that can be assigned to an attribute type. For example, hours should be positive, prod type must be red wine or sparkling, substatus is an integer between 0 and 100. Finally, the ER model also does not support the definition of functions. For example, a function to calculate the average number of projects an employee works on, or to determine which supplier charges the maximum price for a product. The Enhanced Entity Relationship Model, or EER model, is an extension of the ER model. It includes all the modeling concepts, entity types, attribute types, relationship types, of the ER model, as well as 3 new additional semantic data modeling concepts: specialization, generalization, categorization, and aggregation. We discuss these into more detail in what follows. We also provide examples of ER models and review the steps to design an ER model. The concept of specialization refers to the process of defining a set of subclasses of an entity type. The set of subclasses that form a specialization is defined on the basis of some distinguishing characteristic of the entities in the superclass. As an example, consider an artist superclass with subclasses singer and actor. The specialization process defines an is-a relationship. In other words, a singer is an artist. Also, an actor is an artist. The opposite does not apply. An artist is not necessarily a singer. Likewise, an artist is not necessarily an actor. The specialization can then establish additional specific attribute types for each subclass. A singer can have a music style attribute type. During the specialization, it is also possible to establish additional specific relationship types between each subclass and other entity types. An actor can act in movies. A singer can be part of a band. A subclass inherits all attribute types and relationship types from its superclass. Generalization, also called abstraction, is the reverse process of specialization. Specialization corresponds to a top-down process of conceptual refinement. As an example, the artist entity type can be specialized or refined in the subclasses singer and actor. Conversely, generalization corresponds to a bottom-up process of conceptual synthesis. As an example, the singer and actor subclasses can be generalized in the artist superclass. Here you can see how our specialization can be represented in the ER model. An artist has a unique artist number and an artist name. The artist superclass is specialized in a subclass of singer and actor. Both singer and actor inherit the attribute types A and R and a name from artist. A singer has a music style. An actor can act in 0 to n movies. Conversely, in a movie, 1 to m actors can act. A movie has a unique movie number and a movie title. A specialization can be further qualified in terms of its disjointness and completeness constraints. The disjointness constraint specifies what subclasses an entity of the superclass can belong to. It can be set to either disjoint or overlap. A disjoint specialization is a specialization whereby an entity can be a member of at most one of the subclasses. An overlap specialization is a specialization whereby the same entity may be a member of more than one subclass. The completeness constraint indicates if all entities of the superclass should belong to one of the subclasses or not. It can be set to either total or partial. A total specialization is a specialization whereby every entity in the superclass must be a member of some subclass. A partial specialization allows an entity to only belong to the superclass and to none of the subclasses. The disjointness and completeness constraint can be set independently, which gives four possible combinations: disjoint and total, disjoint and partial, overlapping and total, and overlapping and partial. Let's illustrate this with some examples. Here you can see an example of a partial specialization with overlap. The specialization is partial since not all artists are singers or actors. Think about painters, for example, which are not included in our EER model. The specialization is overlap since some artists can be both singers and actors. This figure illustrates a total disjoint specialization. The specialization is total since, according to our model, all people are either students or professors. The specialization is disjoint since a student cannot be a professor at the same time. A specialization can be several levels deep. In other words, a subclass can again be a superclass of another specialization. In a specialization hierarchy, every subclass can only have a single superclass and inherits the attribute types and relationship types of all its predecessor superclasses all the way up to the root of the hierarchy. This figure shows an example of a specialization hierarchy. The student subclass is further specialized in the subclasses Bachelor, Master, and PhD. Each of those subclasses inherits the attribute types and relationship types from student, which inherits both in turn from person. In a specialization lattice, a subclass can have multiple superclasses. The concept where a shared subclass or a subclass with multiple parents inherits from all of its parents is called multiple inheritance. The figure shows a specialization lattice. The vehicle superclass is specialized into motorcycle, car, and boat. The specialization is partial and with overlap. Trike is a shared subclass of motorcycle and car and inherits the attribute types and relationship types from both. Likewise, amphibian is a shared subclass of car and boat and inherits the attribute types and relationship types from both. Categorization is the second important modeling extension of the EER model. A category is a subclass that has several possible superclasses. Each superclass represents a different entity type. The category then represents a collection of entities that is a subset of the union of the superclasses. Therefore, a categorization is represented in the EER model by a circle with a letter U from union in it. The figure shows how the superclasses person and company have been categorized into an account holder subclass. In other words, The account holder entities are a subset of the union of the person and company entities. Inheritance in the case of categorization corresponds to an entity inheriting only the attributes and relationships of that superclass it is a member of. This is also referred to as selective inheritance. Similar to a specialization, a categorization can be total or partial. In a total categorization, all entities of the superclasses belong to the subclass. In a partial categorization, not all entities of the superclasses belong to the subclass. Selective inheritance in this example implies that some account holders inherit their attributes and relationships from person, whereas others inherit them from company. The categorization is partial as represented by the letter P. This implies that not all persons or companies are account holders. If the categorization would have been total, which would be represented by a letter T instead, then this would imply that all person and company entities are also account holders. In that case, we can also model this categorization using a specialization with account holder as the superclass and person and company as the subclasses. Aggregation is the third modeling extension provided by the EER model. The idea here is that entity types that are related by a particular relationship type can be combined or aggregated into a higher level aggregate entity type. This can be especially useful when the aggregate entity type has its own attribute types and/or relationship types. Here you can see an example of an aggregation. A consultant works on 0 to n projects. A project is being worked upon by 1 to m consultants. Both entity types and the corresponding relationship type can now be aggregated into the aggregate concept participation. This aggregate has its own attribute type date, which represents the date at which a consultant started working on a project. The aggregate also participates in a relationship type with contract. The participation should lead to minimum 1 and maximum 1 contract. Conversely, a contract can be based upon 1 to m participations of consultants in projects. Here you can see our earlier HR administration example, but now enriched with some EER modeling concepts. More specifically, we partially specialized employee into manager. The relationship type manages then connects the manager subclass to the department entity type. Department and project have been aggregated into allocation. This aggregate then participates in the relationship type works on with employee. To summarize, an ER conceptual data model can be designed according to the following steps. Identify the entity types. Identify the relationship types and assert their degree. Assert the cardinality ratios and participation constraints, total versus partial participation. Identify the attribute types and assert whether they are simple or composite, single or multivalued, derived or not. Link each attribute type to an entity type or relationship type. Denote the key attribute type or key attribute types of each entity type. Identify the weak entity types and their partial keys. Apply abstractions such as generalization, specialization, categorization, and aggregation. Assert the characteristics of each abstraction such as disjoint or overlapping, total or partial. Any semantics that cannot be represented in the ER model must be documented as separate business rules and followed up using application code. Although the EER model offers some new interesting modeling concepts such as specialization, generalization, categorization, and aggregation, the limitations of the EER model unfortunately still apply. Hence, temporal constraints can still not be modeled. The consistency among multiple relationship types cannot be enforced, and attribute type domains or functions cannot be specified. Some of these shortcomings are addressed in the UML class diagram, which is discussed next. In this section, we discuss the UML class diagram. We start by discussing its origin and provide a recap of object orientation. We then discuss its key building blocks: classes, variables, access modifiers, associations, specialization, generalization, and aggregation. Next, we provide a UML class diagram example. We then zoom in on some advanced UML modeling concepts and conclude by contrasting the UML class diagram versus EER. The Unified Modeling Language, UML, is a modeling language which assists in the specification, visualization, construction, and documentation of artifacts of a software system. UML is essentially an OO system modeling notation, which not only focuses on data requirements, but also on behavioral modeling, process, and application architecture. It was accepted as a standard by the Object Management Group, OMG, in 1997 and approved as an ISO standard in 2005. The most recent version is UML 2.5, introduced in 2015. To model both the data and process aspects of an information system, UML offers various diagrams, such as use case diagrams, sequence diagrams, package diagrams, deployment diagrams, etc. From a database modeling perspective, the class diagram is the most important. It visualizes both classes and their associations. Before we discuss this in more detail, let's first provide a recap of object orientation. Two important building blocks of OO are classes and objects. A class is a blueprint definition for a set of objects. Conversely, an object is an instance of a class. In other words, a class in OO corresponds to an entity type in ER, and an object to an entity. Each object is characterized by both variables and methods. Variables correspond to attribute types, and variable values to attributes in the EER model. The EER model has no equivalent to methods. You can think of an example class student and an example object student Bart. For our student object, example variables could be the student's name, gender, and birth date. Example methods could be calcAge, which calculates the age of the student based upon the birth date. Is birthday to verify if the student's birthday is today. Has passed course ID, which verifies if the student has passed the course represented by the course ID input parameter, etc. Information hiding, also referred to as encapsulation, states that the variables of an object can only be accessed through either getter or setter methods. A getter method is used to retrieve the value of a variable, whereas a setter method assigns a value to it. The idea is to provide a protective shield around the object to make sure that values are always correctly retrieved or modified by means of explicitly defined methods. Similar to the EER model, inheritance is supported. A superclass can have one or more subclasses which inherit both the variables and methods from the superclass. As an example, student and professor can be a subclass of the person superclass. In object orientation, method overloading is also supported. This implies that various methods in the same class can have the same name, but a different number or type of input arguments. In a UML class diagram, a class is represented as a rectangle with 3 sections. This figure illustrates a UML class supplier. In the upper part, the name of the class is mentioned, supplier. In the middle part, the variables, such as supplier number, supplier name. And in the bottom part, the methods, such as getSupplierNumber, etc. Example methods are the getter and setter methods for each of the variables. The method getSupNumber is a getter method which retrieves the supplier number of a particular supplier object, whereas the method setSupNumber newSupNumber assigns the value newSupNumber to the subnumber variable of a supplier object. Variables with unique values, similar to key attribute types in the EER model, are not directly supported in UML. The reason is because a UML class diagram is assumed to be implemented using an OODBMS in which every object created is assigned a unique and immutable object identifier, OID, which it keeps during its entire lifetime. Hence, this OID can be used to uniquely identify objects, and no other variables are needed to serve as a key. To explicitly enforce the uniqueness constraint of a variable, you can, however, use OCL as we discuss in what follows. UML provides a set of primitive types such as string, integer, and boolean, which can be used to define variables in the class diagram. It is also possible to define your own data types or domains and use them. This is illustrated in the figure. The variables subnumber and status are defined as integers. The variable address is defined using the domain address domain. Composite variables, similar to composite attribute types in the EER model, can be tackled in 2 ways. A first option is to decompose them in their parts. In our example, we decompose subname into first name and last name. Another alternative is by creating a new domain, as we did for the address variable. Multivalued variables can also be modeled in 2 ways. The first option is to indicate the multiplicity of the variable. This specifies how many values of the variable will be created when an object is instantiated. In our example, we specified that a supplier can have between 0 and 4 email addresses. Another option is by using an aggregation, as we discuss in what follows. Finally, derived variables, such as age, need to be preceded by a /. In UML, access modifiers can be used to specify who can have access to a variable or method. Example choices are private, denoted by the symbol dash, in case the variable or method can only be accessed by the class itself. Public, denoted by the symbol plus, in case the variable or method can be accessed by any other class. And protected, denoted by the symbol hash, in case the variable or method can be accessed by both the class and its subclasses. To enforce the concept of information hiding, it is recommended to declare all variables as private and access them using getter and setter methods. You can see this illustrated here, where all variables are private and all methods are public. Analogous to relationship types in the EER model, classes can be related using associations in UML. Multiple associations can be defined between the same classes. Also, unary or reflexive and n-ary, such as ternary, associations are possible. An association corresponds to a relationship type in the EER model, whereas a particular occurrence of an association is referred to as a link, which corresponds to a relationship in the EER model. An association is characterized by its multiplicities, which indicate the minimum and maximum number of participations of the corresponding classes in the association. Hence, this corresponds to the cardinalities we discussed in the EER model. This table lists the options available and contrasts them with the corresponding EER model cardinalities discussed earlier. Note that an asterisk is introduced to denote a maximum cardinality of n. In what follows, we elaborate further on associations and discuss association classes, unidirectional versus bidirectional associations, and qualified associations. In case an association has variables and/or methods on its own, it can be modeled as an association class. The objects of this class then represent the links of the association. Consider the association between supplier and product as depicted in the figure. The association class supplies has two variables, the purchase price and delivery period for each product supplied by a supplier. It can also have methods such as getter and setter methods for these variables. Association classes are represented using a dashed line connected to the association. Associations can be augmented with direction reading arrows, which specify the direction of querying or navigating through it. In a unidirectional association, there's only a single way of navigating as indicated by the arrow. The top figure gives an example of a unidirectional association between the classes supplier and purchase order. It implies that all purchase orders can be retrieved through a supplier object. Hence, according to this model, it is not possible to navigate from a purchase order object to a supplier object. Also note the multiplicities of the association. In a bidirectional association, both directions are possible, and hence there is no arrow. The bottom figure is an example of a bidirectional association between the classes supplier and product. According to this UML class diagram, we can navigate from supplier to product as well as from product to supplier. A qualified association is a special type of association that uses a qualifier to further refine the association. The qualifier specifies one or more variables that are used as index key for navigating from the qualified class to the target class. It reduces the multiplicity of the association because of this extra key. Here you can see an example. We have two classes, team and player. They are connected using a 1-to-n relationship type in the EER model, see the upper part of the figure, since a team can have 0 to n players and a player is always related to exactly one team. This can be represented in UML using a qualified association by including the position variable as the index key or qualifier, see the lower part of the figure. A team at a given position has 0 to 1 players, whereas a player always belongs to exactly one team. Qualified associations can be used to represent weak entity types. This figure shows our earlier example of room as a weak entity type being existence dependent on hotel. In the UML class diagram, we can define room number as a qualifier or index key. In other words, a hotel combined with a given room number corresponds to 0 or 1 rooms, whereas a room always belongs to one hotel. Similar to the EER model, UML also supports specialization or generalization relationships. This figure shows the UML representation of our earlier EER specialization with artist, singer, and actor. Note the hollow triangle, which represents a specialization in UML. The specialization characteristics, such as total, partial, or disjoint overlap, can be added next to the triangle. UML also supports multiple inheritance, whereby a subclass can inherit variables, methods, and associations from multiple superclasses. Similar to EER, aggregation represents a composite to part relationship whereby a composite class contains a part class. Two types of aggregation are possible in UML: shared aggregation, also referred to as aggregation, and composite aggregation, also referred to as composition. In shared aggregation, the part object can simultaneously belong to multiple composite objects. In other words, the maximum multiplicity at the composite side is undetermined. The part object can also occur without belonging to a composite object. A shared aggregation thus represents a rather loose coupling between both classes. In composite aggregation or composition, the part object can only belong to one composite. The maximum multiplicity at the composite side is 1. According to the original UML standard, the minimum multiplicity can be either 1 or 0. A minimum cardinality of 0 can occur in case the part can belong to another composite. As an example, consider two composite aggregations, one between engine and boat, and one between engine and car. Since an engine can only belong to either a car or a boat, the minimum cardinality from engine, the part, to boat and car will be 0 respectively. A composite aggregation represents a tight coupling between both classes, and the part object will be automatically removed when the composite object is removed. Note that a part object can also be deleted from a composite before the composite is deleted. This figure illustrates both concepts. A shared aggregation is indicated by a hollow diamond, and a composite aggregation by a filled diamond. We have a shared aggregation between company and consultant. A consultant can work for multiple companies. When a company is removed, any consultants that work for it remain in the database. We have a composite aggregation between bank and account. An account is tightly coupled to one bank only. When the bank is removed, all connected account objects disappear as well. Here you can see our earlier EER HR example in UML notation. It has 6 classes, including 2 association classes, manages and works on. Note the various variables and methods for each of the classes. The access modifiers for each of the variables have been set to private so as to enforce information hiding. Getter and setter methods have been added for each of the variables. We also included a shared aggregation between department and location and between project and location. Hence, this implies that location information is not lost upon removal of a department or project. We have 2 unidirectional associations between employee and project and between department and project. The unary association for the employee class models the supervision relationship. When you contrast this UML class diagram with the EER model, it is clear that the former has a lot more semantics embedded. UML offers various advanced modeling concepts to further add semantics to our data model. In what follows, we discuss the changeability property, the object constraint language, OCL, and the dependency relationship. The changeability property specifies the type of operations which are allowed on either variable values or links. Three common choices are default, which allows any type of edit, add only, which only allows additional values or links to be added, so no deletions, and frozen, which allows no further changes once the value or link is established. You can see this illustrated in the figure. The supplier and purchase order number are both declared as frozen, which means that once a value has been assigned to any of them, it can no longer change. The languages variable of the supplier class defines a set of languages a supplier can understand. It is defined as add only, since languages can only be added and not removed from it. Also note the add only characteristic added to the on-order association. It specifies that for a given supplier, purchase orders can only be added and not removed. The object constraint language, OCL, which is also part of the UML standard, can be used to specify various types of constraints. The OCL constraints are defined in a declarative way. They specify what must be true, but not how this should be accomplished. In other words, no control flow or procedural code is provided. They can be used for various purposes, such as to specify invariants for classes, to specify pre- and post-conditions for methods, to navigate between classes, or to define constraints on operations. A class invariant is a constraint which holds for all objects of a class. An example could be a constraint specifying that the supplier status of each supplier object should be bigger than 100, as you can see illustrated. Pre- and post conditions on methods must be true when a method either begins or ends. As an example, before the method withdrawal can be executed, the balance must be positive. After it has been executed, the balance must still be positive. OCL also supports more complex constraints. This figure illustrates the two classes, employee and department. They are connected with two associations to define which employee works in what department and which employee manages what department. Note the role names which have been added to both associations. Various constraints can now be added. The first constraint states that a manager of a department should be at least 10 years employed. The context of this constraint is the department class. The constraint applies to every department object, hence the keyword invariant. We use the keyword self to refer to an object of the department class. We then use the role name managed by to navigate to the employee class and retrieve the years employed variable. A second constraint states a department should have at least 20 employees. The context is again department. Note that self.workers returns the set of employees working in a specific department. The size method is then used to calculate the amount of members in the set. A final constraint says a manager of a department must also work in a department. From these examples, it is clear that OCL is a very powerful language, which adds a lot of semantics to our conceptual data model. In UML, dependency defines a using relationship, which states that a change in the specification of a UML modeling concept may affect another modeling concept that uses it. It is denoted by a dashed line in the UML diagram. An example could be when an object of one class uses an object of another class in its methods, but the referred object is not stored in any variable. This is illustrated in the figure. We have two classes, employee and course. Let's say an employee can take courses as part of a company education program. The employee class includes a method tookCourse, which determines whether an employee took a particular course, represented by the input variable CNR. Hence, an employee object makes use of a course object in one of its methods. This explains the dependency between both classes. This table lists the similarities between both the UML class diagram and the EER model. Here you can see the table continued. From the table, it can be seen that the UML class diagram provides a richer set of semantics for modeling than the EER model. The UML class diagram can define methods which are not supported in the EER model. Complex integrity constraints can be modeled using OCL, which is also not available in the EER model. In this chapter, we discussed conceptual data modeling using the ER model, EER model, and UML class diagram. We started the chapter by reviewing the phases of database design: requirement collection and analysis, conceptual design, logical design, and physical design. The aim of a conceptual model is to formalize the data requirements of a business process in an accurate and user-friendly way. The ER model is a popular technique for conceptual data modeling. It has the following building blocks: entity types, attribute types, and relationship types. The EER model offers three additional modeling constructs: specialization, generalization, categorization, and aggregation. The UML class diagram is an object-oriented conceptual data model and consists of classes, variables, methods, and associations. It also supports specialization, generalization, and aggregation, and offers various advanced modeling concepts, such as the changeability property, object constraint language, and dependency relationships. From a pure semantical perspective, UML is richer than both ER and EER. In subsequent chapters, we elaborate on how to proceed to both logical and physical design. This chapter is based upon our book, Principles of Database Management. I'm happy to refer to the website at the bottom for more information.